Consider this big race, hoop versus cylinder, or hoop versus disc. Okay, in this case, the hoop, all the mass is around the edges. The moment of inertia is mr squared. The cylinder instead, the mass is spread out through this whole surface. So the moment of inertia is 1/2 of mr squared. The question is, which has the greatest kinetic energy at the bottom? Both of them have the same mass here. You see the same m and the same radius. And they start at the same height. The key here is conservation of energy. What's their mechanical energy at the beginning? Mechanical energy is going to be kinetic energy plus potential energy. Since initially both of them are not moving or rotating, the kinetic energy is 0. And their mechanical energy is just the gravitational potential energy. Now at the bottom, both of them are going to have the same mechanical energy as they had initially, but in this case the mechanical energy is going to be just kinetic energy, not gravitational potential energy, because we are at the bottom. We lost that h. Both of them went down by height h. The kinetic energy is both rotational kinetic energy and linear kinetic energy, but it is kinetic energy. And you notice here it is the same, irrelevant of the shape of the object. That kinetic energy is just equal to the initial mechanical energy, just due to the conservation of energy. However, what about the speed at the bottom? Now it becomes a little more tricky. Kinetic energy at the bottom, what is it equal to? Kinetic energy at the bottom is 1/2 of I omega squared plus 1/2 of mv center of mass squared. Now, if they are asking for the speed, they are asking for v, so let's rewrite this in terms of v. So omega is v over r. So this is going to be 1/2 of I v squared over r squared plus 1/2 of mv squared. Or in other words, I'm going to rewrite it here now. My kinetic energy, which is the same for both of them, is going to be equal to 1/2 of I over r squared plus m times v squared. And v squared is then just equal to 2 kinetic energy, which is the same for both of them, over I over r squared plus m. Both of them have the same mass. So the one that's going to have the larger I is going to have the larger denominator here, so the smaller velocity. So which one has the larger I? The hoop. So since it has the larger I, it's going to have the lesser velocity, so it has the lowest speed at the bottom. So the winner in this case is the cylinder.